Okay, starting now, we finally finished our basic review of calculus analysis, and we'll be going on to our next session, which is new topic, which is called linear algebra. I hope you guys heard about the concept of linear algebra, because even if you haven't, it's okay, but it's used throughout in economics and economic research, so it's very nice to know about it, especially if you took courses in econometrics classes, or maybe some more harder concepts in econometrics. You use a lot of the concept in linear algebra, and you use a lot of matrices and vectors, so it's very nice to get used to it. So we'll be talking briefly about what linear algebra is, and some of the things you should know at least before getting into the graduate course. And also before we start, I want to emphasize that, again, just like the analysis courses, this linear algebra course cannot replace the actual linear algebra courses. So try to take it as a reference and use it to expand your knowledge, and take classes if you have to, or read the textbooks. So just be aware of that. It's just my disclaimer. So we're starting our new chapter, which is linear algebra, as I said. So what is linear algebra then? So linear algebra is basically about mathematics that deals with vector space, linear map, and matrices. I hope some of you guys are familiar with these concepts, especially matrix. So why do we need this in economics? Well, because of many reasons. Because linear algebra, abbreviated to LA, so LA is used a lot in econometrics and also microtheory and a lot of the parts in the field of economics. So that's why we really need to know about linear algebra, at least its basic notations and definitions. And especially you might be familiar with least square estimator in OS regression. That is, if you took some econometric courses, a lot of the times you'll be learning about linear regression. And when you talk about linear regression, you always talk about, you might have heard the term like least square estimator or some concept like that. Actually, if you want to know about what least square estimator mean, like the concept of least square, it actually also comes from the knowledge of linear algebra. That's why you need to know about this, about how it works. So in order to fully understand the concept in econometrics and theory, etc. in economics, you need to know about some basic LA to start. So that's why we're going to have some very brief course about concepts in LA. All right. So where are we going to start? There are many ways to start, but for me, I'm going to start with the system of equations, because I think that's the way we can first see why we would like to use linear algebra concepts. So in economics, we usually encounter some problems with multiple equations. Like our lives would be a lot easier if we have just one sort of equation and we just solve one question. But the problem is there are cases where solving the question where there's a lot of equations that shows you like maybe some like restrictions or some sort of conditions, right? For example, in this case on the slide, you see some sort of equations for starting from y to n. So there are like n number equations you have to solve, right? So each equation is like so we have one equation here. So we have n variables right now, x1, x2, and xn variables. And for all these variables, we have n equations, which is starting from y1, y2 to yn. So like there's like n equations, n variables like this. So the problem is, yes, you can solve it. I mean, if the question was easy as like, if there's just like two questions where x plus y is 3 or 4x plus y is, I don't know, 7, something like this kind of questions. It's kind of easy to see whether it has a solution or not, because what you need to do is just use the substitution and solve two equations. But the problem comes out if there are like 100 equations or maybe n number equations. Then it takes really too much time if you want to do this equation and solve it one by one, right? And even writing it explicitly takes too long time. So it would be very cumbersome to solve these questions separately. That's why the system equations, sometimes you feel like, I don't know how to solve this if I want to solve this by one. So what we do is, but linear algebra comes to rescue, because using linear algebra and the concept of matrix, we can make this equation a lot easier and make it more readable, at least in my sense. This inconvenience can be significantly reduced using a matrix. So remember this equation? Very confusing equation with a lot of equations. But using matrix and linear algebra concept, we can reduce this question into just one equation like there. Ax is y. So you might think how that works. And this is very simple. Ax and y is just like a symbol for the equations we just used. So in the bottom part, I've written like how is it constructed. So firstly, for number A, you can see there's a coefficients inside this matrix. We call this matrix, by the way. There's a coefficient from A11 to ANN, right? Basically. Which is the coefficient we saw in the last slide. Remember that for every axis there were coefficients, right? So basically we put all the coefficients into the A matrix. And for the big X is actually just like another matrix sort of concept, where basically what we have is the n number of variables, right? From x1 to xn. We put it like this. And then for the Y, it's also, we just grouped y1 to yn. So what we did is just make this multiple equation into just one equations. And you can kind of see how it works. You can kind of see that if you make the x part horizontal and put it in on top of A, you can kind of see that if you put this x and you kind of convert it, make it horizontal, and just multiply this, like this part all to x1, this part to x2, on, and this part to xn, you can kind of see you get the formal equations, right? So this is how it kind of works. But you might wonder, so how is this notation working? So what does this notation mean? So what is like this whole matrix thing? So what we saw here, notations like A, X, and Y, we can all call this as matrix. So how are we going to call this matrix? And what are their properties? What is this new definition? So I'm going to give you a very brief introduction. So we call this sort of matrix n by n matrix, where the n refers to the number of rows and m refers to the number of columns. So basically matrix is sort of an array in mathematical term. So if you look at the formal slide, what we saw was for matrix A, we can see that it is in this case it's n by n matrix, right? Because it has n number of rows, it has n number of columns, right? In this case. So we have an n by n matrix, so the rows and columns are the same, right? And for number x, we have the case where it's n by 1 matrix, where there's n number of rows, but just one column, right? And same with the y. So we call these matrices n by n matrices to denote like how many number of rows and columns it has. It's like an array that has number of values inside. So. And as I said, note that we can also use the case where n is 1 or m is 1 or both is 1. So even if you have a matrix where it's just like has just one number here, like A, this is still matrix because this is just 1 by 1 matrix, right? At least in definition. Although we don't usually use a lot of the case where it's like 1 by 1 matrix, but still, it also mathematically means the same thing. So we just need n and m to be positive integers, right? Because we can't have 0 in columns or minus columns, right? So they're going to be positive integers. That's the only restriction it has. And since we have a new definition of matrices, we want to know that how it basically operates in basic arithmetics. So I just wrote down very basic arithmetic concepts such as addition and subtraction, multiplication. So basically, so how are these matrices behave? How are we going to do operations? So first thing we're going to talk about is how do you add up matrices? And it's very intuitive. So for example, let's say in the slide you can see there's a matrix A and matrix B, right? And each part is an element. And just for your information, the indexes in A and B, they denote the the location of their row and columns, right? For example, just for information, you see like the numbers for the indexes. So what this means that this value, this variable, this value, 1, 1 means that it's in the row 1 and column 1. And for this one, it's in row 2, column 2, right? So this like, the indexes denote the location of the values inside the matrix, just for your information. So with A and B, you add it up, and how you get the addition in matrix? And it's very simple. You just add it by value. So you add A11 to B11, A12 to B12. You can see that the values just added by the locations. So basically, you kind of like overlapping them. So you have some variables here. You have some variables here. You're doing addition. You're kind of like putting it on top of the matrices. You're just adding up location by location. Very simple. All right, and since addition is just like inverse process of subtraction, subtraction works also similarly. So, for some warning, so for matrix addition and subtraction, both matrices must have the same n and m. That means that the matrix must have the same row and same column, which is kind of obvious because we saw that basically the addition and subtraction, we're just like adding the variable values by the location, right? So if the row or the column names are different, we can't add them. Like, imagine like a situation where you have like a 1, 2, 3, 4, but if you want to add up this, like 1 and 2, add this up, you can't add this, right? Because where is this going to go? So these kind of stuff doesn't work. All right. So if n and m are not same, the subtraction or addition is not going to be defined in matrix terms. Oh, and just before we talk about basic properties of like matrix addition and subtraction, let me just talk about, I didn't put it here, let me talk about scalar multiplication. What it means is that we have a matrix, and you know like how in a lot of equations, you have cases where if you have x, you do 4x, like call this like you just multiply the value, right? Similarly, you can also multiply some values to a matrix, and it also works similarly. Like if you have a matrix like this, 1, 2, 3, 4, and you just multiply it by 4, there's a value, one value. You just multiply every element. So what this becomes 4. 4 times 2 is 8, right? So this becomes 8. 4 times 3, 12. 4 times 4, 16, right? So it's like this. For the scalar you don't know scalar yet, but if you multiply one value to a matrix, you just multiply it to all the elements inside the matrix. That you should know that. All right. And similarly, if you multiply -1, which is minus, so you're doing like minus A matrix, minus just goes in like this, right? It's also very intuitive, I think. All right. So we know how the addition and subtraction works, and let's talk about some very nice properties and basic properties of these addition and subtraction, which is called in mathematical term commutativity and associativity. So what does this mean? So commutativity basically means you can switch the operation and still get the same value. So like the first one, you can see that A plus B is same as B plus 4, which means that you can switch the element, you can switch the matrix operation, and for summation and subtraction, you're just going to get the same number. It's not going to change. It's very intuitive because we saw that addition was a part where it was just overlapping the variable and adding the values by their locations, right? So if you add it from left to right and right to left, it's not going to change a thing. It has to be the same. And the second one in the equation is the associativity condition, which means is that if you have 3 matrices A, B, and C, you can start from adding from A, B, and then add C. And then you can also go from B plus C, and then go to A plus C. And then it's going to all get the same values. So parentheses doesn't really matter in this case. And in mathematical term, that's called associativity. So just remember that. But unfortunately, matrix addition, subtraction is very easy to understand, but this all changes with matrix multiplication. So if you're not familiar with it, it might puzzle you because it's a concept that's kind of different. It's less intuitive. All right, let's go. So multiplication is going to be confusing for you if you don't know this beforehand. So I'm just kind of hoping you already know how to multiply matrices. I hope, but if you don't know, it's okay. But it might take you some time. But interestingly, matrix multiplication is what makes matrix very interesting, and also make sure all the multiplication beforehand works. So what I mean by the second part is that, remember we did this, ax is y. You can kind of see that we did the matrix multiplication, ax. And for this to work, we have to have this sort of definition of matrix multiplication, which we're going to talk about. Okay, so I'm going to start by giving you examples. So let's consider like two matrices, A and B. And we're going to assume that the multiplication result is going to be C, right? So we have A and B, which are 2 by 2 matrices, and we're going to do some multiplication. So we want to calculate AB. We perform operations false, like that. So C11 2.5 plus 1 minus 1 times minus 2 is 12, something like this. And you might wonder, how is this happening? So what are we doing? How are we doing the matrix multiplication, and how is this working? But I'll tell you after this. And the resulting matrix is C. So we get this sort of stuff. And you can kind of realize that the multiplication is kind of different. We're not like multiplying the variables like one by one in their location. We do something different. So what does this mean? So you can kind of see, like, as you know, I'll write it. So A is like, what we're doing is, we have A, which is 2 minus 1, 3, 4. And we have B, which is 5, 0, minus 2, 7, like this. And we want to get a C. And what we're going to get here is that we're going to also get a 2 by 2 matrix. So we have 4 slots, like here. So how are we going to get this? How are we going to get each element? And there are a lot of ways to do multiplication, but I'm just going to tell you the way I learned in my high school. So just try it with me. So easier way to do is, usually when you have two matrices, when you're multiplying them, you draw a line between them. So for the left one, you draw horizontal line in the middle. And for the right one, you just draw vertical line like this. Yeah. So what we're doing is, remember that the C11, what we got was 2 times 5, and then we did 1 minus 1 times minus 2, and we added them up, right? And let me tell you where this comes up. So why is this part doing that? This is C11, right? C11. What we're doing is, we draw the line, and for this part, we multiply this by this, and this by this. So we're kind of doing like a row and column multiplication. So for every left part, we just draw a horizontal line, and this part we draw a vertical line, and just multiplying element by element here, and then adding them up. So 2 times 5, right here, 2 times 5, and then we have minus 1 times minus 2, right? Minus 1 times minus 2. And we add them up to get, what did you get? 12, right? And we get 12, right? And we put 12 here. Then intuitively, you can see where this part's going to go. You're adding, for this one, we do here, here. So 2 times 0, minus 1 times 7. So we get 2 times 0 is 0, minus 1 times 7 is minus 7, right? And go like this. So kind of way, what we're doing is that when we draw a horizontal vertical line and we're doing multiplication, because this is first row, right? We're doing the first row and we're multiplying the first column, you get 1, 1, which is C11. And for C12, we do first row to the second row, 1, 2, right? To this. And for C, I'm not sure if you can see this, but for C21, second row, first row, right? So 3 times 5, 15. 4 times minus 2, minus 8, that's 7, right? I'm not good at calculations. 7, yeah, okay. And then C22, we get 3 times 0, 4 times 7, and 28. And that's the multiplication, right? And you might think that this is easy because it's just 2 by 2, right? But this sort of process works similarly for any sort of size matrices. So later on, if you have a case where there's like a, I don't know, I mean, if there's like a, for example, 2 by 2, right? 2 by 2, 2 by, let's just do 3 by 2. Maybe there could be cases where we can also do multiplication like this. So even in bigger cases, like when the matrix here is 3 by 2, and the second matrix is 2 by 2, we're doing multiplication. What we're doing is, so this is 3 by 2 matrix, and this is 2 by 2, right? We also do is we draw a line. We draw line, 2 lines now, and we draw 1 line for here. And similarly, we do the same thing. If I want to get a value for C, so first row, first column. So 2, 5, minus 1, minus 2, which was 12, right? It's the same. And 2, 0, minus 7 is going to be minus 7. Right. And 3, 4, 5, 2. So second row, first column, you get 15 minus 7. And this is 28, right? Because second row, second column. So like 1, 1, 1, 2, 2, 1, 2, 2. And now we have the new part, new row. So where's this going to go? So third row, first column. So third row, first column. 3, 1. It's going to be here. So 1, 1, 1 minus 2. So it's 5, 3, right? 3. And 1, 1, 1, 1 is 7. So you can kind of intuitively see the multiplication process is like, for the left side, you multiply the row. Second matrix, you multiply the column. And using that, this gives you like the index for the multiplication. So second row, first column, you put it here 2, 1, like this. And third one, second row, third row, second column, 3, 2. And you can kind of see also, I'm going to explain this later on the slide, that this is 3 by 2 matrix. And this is 2 by 2, right? You can kind of see that you're getting C is 3 by 2 matrix, right? And what we can see is that actually we're kind of merging them. 3 by 2, 2 by 2. So we're merging this part. And we're only left with this 3 and 2. So later I'm going to tell you, if you multiply 3 by 2 matrix, for example, to 2 by 1 matrix, you're going to get 3 by 1 matrix. When you multiply 2 matrices, you're left with the outer parts as your row and column. So if you multiply, for example, 2 times 4, 4 times 1 matrix, if there is one, you're going to get 2 by 1 matrix on the outside. And writing this, you can kind of guess already that in order to multiply the matrices, let matrices number of columns and right matrices number of rows has to be the same, right? Otherwise, it's not going to work. So I'm going to talk about this also in the slide. Okay. That's how it works. Any questions? Before we move on, just a quick question. 고등학교 때 행렬 들으신 분 있나요? 행렬 배우셨다. 아, 많이 배우셨네요. 아, 저와 동기. 아마 제가 대학교 가고 얼마 안 돼서, 그러니까 대학 가고 아니라 제가 거의 마지막으로 행렬 배운 쯤으로 알고 있어서. 근데 확실히 고등학교 때 행렬 배우셨으면 좀 익숙할 수 있습니다. 확실히 고등학교 때 행렬 배웠으면은 행렬 곱하고 이런 게 좀 익숙해서 좀 익숙하실 수 있는데, 만약에 처음이면은 아마 이제 선대 수업 안 들었으면 사실 이제 행렬을 볼 일이 거의 없어서 조금 헷갈릴 수 있는데, 행렬 곱이 이런 식으로 되고, 아마 제가 한 방법도 아마 고등학교 때 행렬을 들으셨으면은 익숙할 곱하는 방식이죠. 여러 방식들이 있지만. Okay, now moving on. I just wrote this not to like make you memorize this. I just wrote it to make sure that there is a more abstract definition. It's like this. So basically, we have an A which is M and M matrix, and B is an M by P matrix. From here, you can already see that for a matrix to work, the left-hand side matrix has to have the same, the column number for matrix A has to be same as the row number matrix B, right? Because two matrices, the same thing is the N part, right? You can kind of see how that must happen in order for matrix to work. And their product matrix C, which is results from the multiplication of A and B, becomes M and P matrix. So you already see that when you multiply them, only the outer part survives. So you multiply M and N matrix with N and P matrix, and you're just getting outer part, which is M and P matrix, M by P. So that's how it works. Also, it's like a good way to check if your multiplication is correct, because if you did a multiplication and you're not getting the matrix row number and column number that you got, that means you're wrong. So you have to recheck your work. So it's kind of like a nice tip. So for each indexes of the multiplication matrix C, you have to do this, right? It might look really confusing, but this just basically means what we did right now. Before we multiplied the we multiplied the row section with the column, right? That's what we have to do. Just written in a more rigorous mathematical form. That's what we did just before. So I just wrote like what AIK and BKG kind of mean. So basically I said the AIK, where the IK is like an index that shows that the element is in the ith row and kth column, and BKJ is the element in the kth row and jth column. CIJ is like ith row and jth column. So when you're indexing the elements inside the matrices, we use these sort of index notations. So in other words, like in order to calculate the element in the ith row and jth row of the product matrix C, we're kind of performing like a dot product. So you might not know what dot product is, but it's just same thing we just did with our examples. That's kind of doing dot product. So we're basically doing like a dot product between the ith row of the matrix and the jth column of the matrix. See? So if you do multiply ith row of matrix A with the jth column of the matrix B, we're going to get an element in the ith row and jth column. So that's how we do it. So I just gave you a bit more abstract definition. Any questions until this point? If not, I'll move on. So learning some very interesting properties is that you can see that if you multiply two matrices, if the number of columns on the left-hand side equals the number of rows of the right-hand side matrix, which is what we just did countless times, right? Okay, they have to be the same. So when you multiply them, you're going to get a new matrix with number of rows that equals that of the left-hand side, and with number of columns that equals that of the right-hand side. That's what we also said. If you multiply two matrices, you're going to get the outer parts as your row and columns. So, but the part is we only did like very easy computations. And I don't know, I mean, if you took like a lot of linear algebra courses or maybe some courses in department in mathematics, you can realize that there are a lot more confusing matrix multiplications processes. So it's very important to get used to the operation of matrix multiplication because you'll be doing them a lot. Even if you're not doing them by hands, you'll have to think about how the operation is going in your head. So unless that, there's going to be some problem that might come up when you're doing your research and your mathematical calculations. So just remember that. And as always, even I don't do this often, but practice is the key. So just, in order to get used to the matrix multiplication, the only way is just do it a lot. So, unfortunately, even though matrix multiplication is a very nice property, it has one of the very sad parts, which is what we thought was very basic and very obvious does not hold. The first one is, well, AB and BA can be different. So basically what it is, I mean, you can also check in the example we did on page 8, but you can also kind of see already because how there was a, let's say it's like 1 by 3 matrix and 3 by 2 matrix, and let me just, for example, should be 1 matrix. 일로. If you multiply 1 by 3 matrix with 3 by 1 matrix, what we're going to get is 1 by 1 matrix. So it's just going to be one value. But switch it. So switch it and try to multiply 3 by 1 matrix with 1 by 3 matrix. You're going to get 3 by 3 matrix. It's not going to be same. You can already see this. But this doesn't mean that it only this kind of problem only holds when there's like different row number and column numbers. Even if the row number and column number are same, there are cases where AB is not going to be same to BA, right? Even if this was like 2 by 2 matrix, 2 by 2 matrix. So even if you switch, you're still going to get 2 by 2 matrix, right? But even if that works, there could be parts, there will be some times where if you switch the multiplication, they're not going to be the same. So our nice property, commutativity, is not going to work for the multiplication. All right. So generally it does not work. But fortunately, associativity does. So if you multiply ABC, 3 matrices, if you do AB first, or if you do BC first, it's the same. It's not going to change your output. So, okay. So, let's move on. So, going back to the system equations. So, this is the reason using the matrix multiplication. That's why we can use it to write system equations like AX and Y. So in a way, matrix is a good way to reduce our complex calculation in one line. That's why we use this. But the problem is this the only benefit of using matrix? So are we using matrix just because it's good for convenience in calculating multiple equations? And you can kind of guess that's not going to be true. And we'll see how it goes out. I'm not going to explain much about this in this session, but I'm going to talk about this very briefly in the next section. But matrix is also a special kind of function. So what I mean by a function, actually you can kind of guess it from the definition of how we did this, like y is ax. You can see this is kind of like similar to function, right? We did a, but kind of we can just say this is fx, right? So you can kind of see that the matrix is also a function. It's a special type of function, that is. All right. So matrix is going to be a very special case of a function. And to be more exact, matrix is a linear function mapping vector spaces. So what the hell is vector space, you might think about. So what is this vector space? So because we have to talk about this concept called vector spaces now, we need to know more about the fundamental elements of linear algebra. Remember we talked about why we learn real numbers and basic topology in analysis courses? Because we need to know about the spaces we're in, so we can talk about the function that deals with these spaces, right? Similarly, we talked about matrix, but in order to know more about matrices, we have to know what space it's on. And then for linear algebra, that's vector spaces. So we're going to learn a bit more about vector spaces from now on. But before we start, we're going to have a short break for 5 minutes. And then after that, I'm going to talk a bit more about the vector space. And then about 40 to 50 minutes, we're going to have a lunch break, okay?